Thanks. I'll begin with a word of prayer. Dearly Father, we thank you again for this opportunity we have just to meet together and to study your creation. I just pray to be with us today. Help us to, again, Lord, glorify you and what we do, Lord. In your name I pray. Amen. So, Monday, listen to me. Tuesday, I showed you guys, the technique for finding solutions to the homogeneous problem, right? But basically today what I want to do is take a step back and so my notes, section 3.1 of my notes, I have this sort of theoretical discussion, like what's the structure here, what are the possibilities, what are we looking for basically. And so let me just kind of get that. It should take me about a half hour to tell you guys, and once we're done with that we'll get back to computations. But here it is. So, A naught, the nth power of the differentiation operator, plus A1, the n minus 1th differentiation power, differentiation operator plus plus, how's it go? Make sure I got my numbering right. Yeah, I sporadically I number these, if you look at different stuff I write, sometimes I'll number these one way, sometimes I'll number them the other way. It's not terribly significant. Sometimes I'll go from, and then I'll regret my life because I'll try to compare them, but you should be aware, beware, I should say, that sometimes I'll number these n minus 1, A0, like that. So, anyway, we can go either way, but I'm just going to choose this as the labeling today. Now this, what is this? Here, we have A naught, A1, AN. These are actually going to be functions on some interval, which is a subset of the real numbers. All right, so like last time I showed you how to solve this thing, right? When we had the case g equals 0, and so like last time, just to sort of summarize what we did last time. So last time we had g equals to 0, and we had A naught through AN real numbers. In fact, we had A naught equal to 1 in my last talk with you guys. Now, if the g is 0, this makes the equation what's called homogeneous. So we studied homogeneous nth order, constant coefficient ODEs last time. I showed you how to solve those essentially by looking at the so-called characteristic equation and factoring it. Actually, I looked at it in terms of factoring operators, but more on that later. So, so what I've written at the top is, this is basically the definition of nth order. This is an nth order linear ODE on the interval I. Okay? And so I just want to communicate to you guys what the theory is for this problem. All right? So like, first of all, there's a theorem. All right. Well, I guess first of all, if I call this thing, it just needs to do some name calling here. Let's call this whole thing, this whole operator, let's call it L, right? So we have L of y is actually like A naught, the nth derivative of y, right? Plus A1, the n minus 1th derivative of y, plus an minus 1 y prime, plus an times y equals to g. So that would be the notation. Oftentimes we see the differential equation in the prime notation, right? Not in the operator notation, just to go back to that. So, little property here that you can see from just basic calculus, little observation. And this is what's called superposition. All right. If we have L of y1 equals to g1, and if we have L of y2 equals to g2, all right? So let me sort of give you a physical interpretation for what's going on here. G is like it's called the forcing term. If you look at the case that L is actually like Newton's equation, G takes on the interpretation of an external force. So what this data we're looking at is saying, this is the solution if you apply that external force. This is the solution if you apply this external force. All right? The method of the superposition principle says that if you look at a linear combination, so like C1y1 plus C2y2, well, what you get, all right, because L is a linear operator, you get C1 L of y1, right, plus C2. Now, I mentioned to you guys that the constant coefficient case is a linear operator, but this L is also a linear operator because differentiation is linear. And the constants in front, like the A naught through AN, they just kind of ride along. I could write it out. It would take 10 minutes. It would be a lot of writing. You guys believe me that this is true? I hope. But then what? This is what? This is C1G1 plus C2G2, right? So in other words, if you want to analyze a system that's linear, if you can look at the net forces on it, right? You look at the net force. If you can rip apart the net force into a sum of individual forces, then the net response of the system is a sum of the responses to the individual causes. So you can look at what's going on as a sum of the parts, basically. So linear systems are nice because they allow you to sort of divide and conquer the problem solving in this sense. So you're not going to have like a spring mass system and I have two different forces on it, two separate forces. They're both put on it at the same time. I can take off the one force, find out the response, right? And I can put the other force on it, find out the response. The sum of those two responses will be how the system behaves when you put both forces on it at once. That's superposition. Let me be a little bit more specific here before I get into the further theory. So for example, we could check it out. So like y prime prime plus y equals to x, and I could solve y prime prime plus y equals to e to the x. These are sufficiently simple. You guys can probably guess the solution for me. This would say, I'm going to say yp1, p for particular. Yp1 equals what? That's just a label. What's solve this one? I'll do the easy one. I'll let you guys do the hard one. Second derivative is 0, right? So if I want to get back an x, I can just put, this is really almost too easy. X. Yeah. As we go to more complicated problems, that is not going to work for us, okay? I mean, we just were able to just guess that that's the solution, right? It's a solution. It's not the general solution, as we'll see. And let's see here. Y prime prime plus y equals, well, to get back in e to the x, what could I do? What if I tried e to the x this time? Since we got so lucky with the x, let's try e to the x. What happens? Y prime prime gives you back, differentiate e to the x two times, you get back e to the x, right? Yeah, we'd get 2 e to the x, so what do we got to do? Divide by 2, right? Now you have some homework problems, like a homework problem, where they basically give you yp1 and yp2. They tell you, hey, this is a solution to this differential equation, and then they're like, solve a corresponding problem that's related by superposition. So we could solve y prime prime plus y equals to like 3x plus 2e to the x. So given that result in superposition, I know that a particular solution would be 3 times x plus e to the x, because that's 2 times 1/2 using superposition. Then you can check it. You can differentiate that 2 times, add it to itself, you'll get back 3x plus 2e to the x, which shows that in fact it is a solution, a particular solution. Okay, so that's superposition in a nutshell. Very important, very important feature of linear systems. If you don't mind, I'm going to erase this and write the theorem I'm interested in right under that. Well, actually, even if you mind, I'm still going to do it. Truth in advertising here. Let's see here. So I usually regret writing this theorem, but let me just write it. It'll take 2 minutes of my time, and then it'll be written, and we can talk about what it means. So, theorem. So this is existence and uniqueness. That was supposed to be there. Fine, fixed. So here we go. We suppose that we have continuous. Oh, if you don't mind, I had an F here instead of a G. I'm going to just adapt the theorem a little bit. So let's suppose we have A0, A1, dot, 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 AN, and G. Continuous. You guys know what continuous means, right? Okay, so continuous on I. And A sub naught of x is not equal to 0 for each point in the interval. So basically, the differential equation has continuous coefficient functions, and the leading coefficient is non-zero in the whole interval. All right. If the leading coefficient dropped to 0 somewhere in the interval, that would mean there it's not really nth order anymore, right? This being non-zero makes it genuinely nth order. Does that make sense? So if you got all that, and you have then a point in I, and constants, n constants, y naught through yn minus 1, given a point in the interval that the differential equation is defined, and an initial data set. So initial data, all I mean by that is just n constants, all right? So y naught, y1, da da da, yn minus 1, real numbers, given real numbers, okay? Given this data. Then there exists a unique function let's say phi, from the interval back to the reals again, such that L of phi of x is equal to g of x for x and I. In other words, and of course L, I'm still using that notation up there, right? In other words, this is saying that y equals to phi is a solution. And more than that, more than it just being a solution, right? What is this phi? I mean, it does certain things, right? One, it's a solution. And two, it matches the initial data in the following sense. Phi of x naught is equal to y naught. Phi prime of x naught is y1. Phi prime prime of x naught is what? y2, all right, yeah. And so on you go. So on it goes, all the way down. The n minus 1th derivative at x naught is equal to y sub n minus 1. So in other words, if you have continuous coefficient functions with leading coefficient identically non-zero on the interval, not only can you find a solution, you can find a solution that matches any set of initial data that you like, and the solution exists on the whole interval. This is really quite fantastic, this theorem. We will not prove it in here. It's proved in chapter 13 of your book. But that's kind of a fundamental building block we have in here, all right? So what does this basically say? It says the problems we're looking at can be solved. And they can be solved in a pretty nice way too, right? Excuse me. Now, we need a concept in here that might be new to you. Definition. Functions, let's say y1, well, maybe I should let me use f's for a second here. What did I use in the notes? Let me be consistent. I used f's. All right, so let's say f1, f2, fm are linearly independent on I, all right? So these guys all include I in their domain, all right? If you like, you can assume that their domain is I, if that's helpful to you. All right, so to say that they're linearly independent, what that means is that they're, it's okay, generally distinct functions. So if they're not linearly independent, they're linearly dependent. And what that means is that you can write one as a multiple of the other, as a linear combination of the remaining ones. So a convenient way to characterize linear independence is just this. If you take a linear combination like C1 F1 plus C2 F2 plus plus Cn Fm, if that's equal to 0, all right, then that implies that C1 equals to C2 equals to equals to Cm is equal to 0. In other words, if we take an arbitrary linear combination of the functions and you set it equal to 0, it implies the coefficients are 0. This is, you should be aware, it's a little bit sneaky. This is a function equation. So what this really means, all right, this is shorthand for something a little bit more complicated. That's an M. And for what x? It has to be 0 for each x. In the interval of consideration. So I can't talk about linear independence of a function, a set of functions, without reference to an interval. Linear independence of a function there has to be a common interval which we're referencing. All right. If you've had linear algebra or you're taking linear algebra, and there we look at things which are just sort of static. There's no interval you have to play around with. Let me kind of find out. Let me just get out of my system. Here's a stupid and subtle example. So for some example, I'll start with an easy example. E to the x and 2 times e to the x are not linearly independent. So Li is linearly independent because I get sick of writing linearly independent like 300 times in this course. So Li, linearly independent. Not linearly independent is also called linearly dependent. Okay, so what's the linear combination that gets you 0 but doesn't have coefficients which are 0 for these guys? Let me start us out. So we've got, I'll do the coefficients in green. I do like -2, right? And then +1. And then my functions, e to the x and 2e to the x. As you can see, this is like my C1, this is my C2. If you add these, we get 0, right? For all x in the reals. I'm sorry, I just used an upside down A. Do you guys know what that means? That means for all. It's just math speak for all. So just shorthand. But as you can see, there's a non-trivial linear combination of those functions which gives you back 0. The domain of consideration here, like I've already violated my first tenet, not linearly independent doesn't make sense, right? So In something like this, if you say that, what do you mean? With respect to what interval? So I guess, there's a custom that if there's a common understood domain for both, you just are talking about it with respect to that. But this leads to confusion. To be really careful, we should state the interval. There are functions which are linearly independent or linearly dependent, depending on what you choose the interval of consideration to be. Let me show you a stupid example. Before I get to that, though, for two functions, to judge linear independence, you can just check is one a multiple of the other, which is pretty nice. So for two, in fact, another way to look at that is if you can take the quotient of the functions, like if you take the fraction of the functions, if that's a constant, right, they're linearly dependent, because that means you can write one as a multiple of the other. On the other hand, if you divide the functions and it's not a constant, then it doesn't have to be, they could be linearly independent. Right? Okay, so here's my sort of stupid subtle example. If you look at the set x, comma, absolute value of x, this is either linearly independent or linearly dependent, depending on what interval of consideration you have. See, this is linearly independent on the reals, but it's linearly dependent if you just look at the positive reals. Right? Because well, basically they have different graphs. Over here, of course, we have, on the positive reals, we just have the absolute value of x is equal to what? X. Oh, wait a minute. Sorry, all of a sudden I'm doubting myself, but no, this is linearly independent over here on the whole reals. So let's just suppose you have C1 times x plus, let me just work it out for a second here, so you guys, C2 absolute value of x is equal to 0. And suppose this is true for each x in the reals, right? You're like, but the absolute value of x is either equal to x or plus or minus x, right? Okay, true. So let's see here. So if we put in, let's just work it out. Put in x equal to 1. What do you get? Right? Put in x equal to minus 1. What do you get? Minus C1 plus C2 equal to 0. Add these equations. What happens? We get 2C2 equals to 0, right? So therefore C2 is equal to 0. And what else? Then you get C1 is equal to 0. Therefore, x and the absolute value of x are linearly independent. If you have an interval which includes both positive and negative numbers, basically. The thing is, for them to be linearly dependent functions, they have to be related in the same way over the whole interval. Like x and absolute value of x, they're related, but they're related in different ways on different parts of the interval. Like where the positive, they're just equal, right? But on the negative, they're negative. So there's a different linear dependence on different parts of the domain. That suffices to prove linear independence. Linear independence is really, really subtle. Linear independence of functions, like if I have, this is my one function, right? And my other function is just the same, right? And I just take one point and put it up here. Those are linearly independent. Linear independence means they have the same stupid graph or like a multiple of it. It's quite subtle. All right. Linear independence it's a pretty strong criteria. So this obviously could be confusing, but it won't be for us, all right? I've already said too much, so I'm sorry about that. So obviously we'd like some kind of like nice criteria to test for linear independence, right? Because we're not math majors and this kind of thing doesn't delight us too much. We really want a formula, right? So let's work on deriving a formula for linear independence. Let me show you how it goes. So So let's assume that we have, let's say, y1, y2, yn linearly independent, okay? So that means we have c1y1 plus c2y2 plus plus cnyn equals to 0 implies what? So if you have a linear combination equal to 0, it has to be the trivial combination. Them's the rules. If it's a linearly independent set of functions, that's how it works. But it's really nice. It's more than just that, right? We also know that these functions, we're going to assume that these functions, that holds for all x in some interval. And also we're going to assume that these functions are differentiable functions. They're at least n minus 1 times differentiable functions, okay? Suppose that. That means we can differentiate this equation. You guys like differentiating, right? So differentiate this equation, what does it give you? c1y1 prime plus c2y2 prime plus plus cnyn prime equals to, well, derivative of 0, still 0. We enjoy differentiation. Having done it once, we can't help but do it again, and 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 again. So you keep doing this until finally you get to the n minus 1th derivative. You're like, well, why did you just differentiate just n minus 1 times? Well, I have my reasons that will become quite obvious in a second here. Now, you may or may not have had linear algebra at this point. We're going to learn some linear algebra in here if you haven't had it. We don't do anything terribly fancy in here, really. Just some basic matrix multiplication, a little bit of eigenvector stuff, but we will learn what we need along the way here. So we can rewrite this as a matrix multiplication, in fact. So maybe you've seen matrix multiplication in like your high school algebra course or something. Maybe you haven't. If you haven't, you'll just have to take my word for it. So if I want to rewrite this, I've got the same I've got the same C1. The C's are the same everywhere, and every one of these C's are all the same. So I can always pull the C's over here, like this. And like the first equation gives me the first row, which is C, y1, y2, yn. That's from the first equation. Right? The second row, y1 prime, y2 prime, yn prime. Right? And you just keep going. The nth row, that's why I differentiated n minus 1 times, is so that I would have a square matrix here. So we get this square matrix of the functions and their derivatives. All right? So this is what's known as the Wronskian matrix. The Wronskian matrix of the functions y1, y2, yn. We're assuming linear independence of these functions, right? So what's the solution of this system of linear equations? What's the solution to the system of linear equations? Well, we're assuming these are linearly independent, right? The only solution to this system of linear equations, right, is the zero solution. There's a unique solution of the zero solution. So how many of you, has anybody in here had linear? Anybody? Couple. So you guys tell me, what does it mean we have AV equals to 0. Let me put a C here because we got this constant vectors. AC equal to 0 only implies C equals 0 is the only solution. What does that say about the matrix A? You should be able to tell me like a few different things about it. It has linearly independent columns, right? It has rank n. It's invertible. None of those things are a formula. We're after a formula. How about this? What's the determinant of A? Is it 0 or is it non-zero? What are they teaching you guys in linear algebra these days? Just started. I mean, just started is fine. If you're just started, you should know this. You guys just started linear or you've had linear? Long time ago. Okay, so one of the things we must remember is that if we have a unique solution to the homogeneous problem, that means that A is invertible. A inverse exists, right? And that is equivalent, in particular, to the determinant of A being not equal to 0. So the fact that this only has the 0 solution forces the Wronskian matrix to be invertible, but more to the point, it forces the determinant of the Wronskian matrix to be non-zero. So linear independence, so that gives us a definition, the Wronskian of y1, y2, yn at some point x is equal to the determinant of the Wronskian matrix at x, where the Wronskian matrix is this thing. All right. Now I know some of you guys, I mean, obviously you probably don't know how to calculate a determinant at the moment. I don't know, maybe you do though. So for example, if we go back to my first example, y equals e to the x and y2 equals e to the 2e to the x, the Wronskian of these guys, right, it's going to be the determinant. So we put the functions in the top row, and then we take the derivative to get the second row. What's the derivative? Well, these are really kind of stupid. I'm sorry, I have to come up with a better example for us. Yeah, so you guys should recall the determinant of A, B, C, D is AD or learn. Recall or learn, I don't care which. Anyway, know it going forward. The determinant of 2 by 2 matrix is multiply the diagonal elements and then the product of the off-diagonal elements, put a minus like that. That's the determinant of a 2 by 2 matrix. That's the pattern. So here, this is equal to, 2 e to the x times e to the x minus 2 e to the x times e to the x. It is 0. That's a little bit subtle here, actually. The fact that the Wronskian is 0 doesn't generally imply that the functions are not linearly independent. You're like, but you just showed that if the functions are linearly independent, it forces the Wronskian to be non-zero. So how is the opposite of that not just... It's because there's also this for all x thing riding along, all right? So like the cautionary tale, the thing we just did, I would just point out, if you look at the Wronskian of x and absolute value of x, which we've just proved are linearly independent, right? What's this give you? You're like, you can't differentiate absolute value of x. Oh man, you're right. I can't apply the Wronskian here. Curses. Oh man. Well. Fine. Here, the different example, y equals x squared, y2 equals to x absolute value of x. So if you look at the Wronskian of this, You got the determinant of x squared, x absolute value of x. I don't know if you ever thought about x absolute value of x before. It's really cool. What it is it's the parabola this way, and it's minus the parabola over here. So it looks like a cubic. It's not quite, though. This is y equals x squared. This is y equals minus x squared. This is, in total, the graph of y of x absolute value of x. It's an important counterexample function in these kind of discussions. The example goes back to like Peano, a great 19th century mathematician. This is in like papers of professional mathematicians in like 1890, something like that. But anyway, the derivative of x squared, you guys know that, 2x, right? And the derivative of this, if you look at it, it's 2x over here, it's minus 2x over there. In fact, it's twice the absolute value of x. So it happens. You can verify that case-wise if you like. But you multiply these, what do you get? You get 2x squared absolute value of x minus 2x squared absolute value of x. This is equal to 0 for all x, right? For all x in the reals. But you can easily see from graphical reasoning, if nothing else, that the function in red is not a constant multiple of the function in green. Right? They're linearly independent functions. They do not have the same shape. If you're just comparing two functions, the question of linear independence or linear dependence is the question, is one function a constant multiple of the other? Are those constant multiples of one another? No, they're linearly independent. Yet the Wronskian is 0 everywhere. The reason it's 0 everywhere is because it's 0 for one reason one place and it's 0 for another reason another place, which is, So how can we avoid this? Then you're like, well, I thought you were just telling me that this formula is going to be the answer to all our problems about linear independence, but it seems like it's not because of this. So like, what's the workaround? Something beautiful happens. For solution sets to differential equations, the naive idea about the Wronskian is true. For solution sets to differential equations, the Wronskian, you have an nth order differential equation, and you have n functions that solve it, all right? The Wronskian is 0 only if the solutions are linearly dependent. And the Wronskian is non-zero. Well, the Wronskian being non-zero implies linear independence in general. That's not subtle. We work that out. But when the Wronskian is 0 for a solution set to a differential equation, that does imply linear dependence. That comes from something called, from what's known as Abel's theorem, which I have proved in the notes. I guess I'm going to project it for you guys in a second here. Before I do that, let's work out another example. If we look at the Wronskian of cosine x and sine x, what do you think? Are these going to be linearly independent or linearly dependent? So you guys can differentiate sine and cosine? By the way, guys, this is not just some esoteric math discussion in here. This Wronskian matrix comes up in formulas that we're going to study to solve explicit applied problems. Like, I'm not just doing this because I love it, although I do. In fact, this generalizes for differential equations over in algebra. You can replace these with functions over in algebra rather than just real value functions, and it still all goes through. I worked that out this summer, but that is somewhat beyond the class. Let me behave. So cosine squared x plus, hey, you guys know what this is. We have what? 1, yeah. Do you guys know about cosh and sinh? You're like, why do you have to bring those into this? And we're doing everything in x. Let's throw a t in. All right, there we go. What's the derivative of cosh and sinh? What are sinh and cosh? Did I tell you guys yet?
I can tell you what the name is. Can't tell you really what they do.
Oh, okay. Well, so basically here's the deal. You take the exponential function, right? And you can rewrite it like this. What did I do? I've just added 0, right? I added and subtracted e to the minus x. I took 1 and split it into a half plus a half. These are very special things. This is, if you replace x with minus x, you get back to where you started, right? This, if you replace x with minus x, you get minus what you started. This is even. This is odd. This is, by definition, the cosh, hyperbolic cosine of x. And this is, by definition, the hyperbolic sine of x, sinh x. These come up as we solve problems this semester. It's important for you to know about them, otherwise you won't understand certain discussions here and there. They're a better way to write solutions in a certain case. More on that later. The point is, those are the functions cosh and sinh. They're the even and odd parts of the exponential, respectively. The derivative of cosh is sinh. The derivative of sinh is cosh, no minus. That's it. And if you look at e to the x times e to the minus x, that gives you cosh x plus sinh x times cosh x minus sinh x. See, the equation above is that e to the x is equal to cosh plus sinh. So that's e to the x. Sinh is odd, the minus pulls out. Cosh is even, so the minuses get absorbed. So this is like e to the minus x is cosh minus sinh, right? What's this? If you allow me this small manga-style calculation. Yeah, 1. So on the other hand, this is what? So we got cosh squared x minus sinh squared x. This is the... So basically, those are your fundamentals for cosh and sinh if you haven't seen them before. There's, of course, more to say, but those will get you a long ways if you know that much. All right? All right, now that I have given you this crash refresher in cosh and sinh, let's go on with our example, if there's not a question. Cosh and sinh are to hyperbolas just like cosine and sine are to circles. That's why they're named so. They have interesting applications in special relativity, among other things. But anyway, so the derivative of cosh is sinh. The derivative of sinh is cosh. And so what we get is cosh squared t minus sinh squared t. Ah, what do you know? It's 1, right? So what these two things show you is that on the one hand, cosine t and sine t are linearly independent, but also the second example gives us that cosh t and sinh t are linearly independent. And to be clear, they're linearly independent on the reals, right? But we can, if you guys want to, we can make an agreement amongst ourselves that if we say linear independent without qualification, we're talking about linear independent on the whole reals. Is that okay? Okay, good. Yes?
And just be clear, we know they're linearly independent because their Wronskian was not 0.
Right, Wronskian is 1. And where I come from, it's not 0. So, doodly doodly. Okay, so. Any questions before I wake the beast? Go for it.
We're just asking about the Wronskian when it is 0. Does that mean it's dependent or sometimes dependent?
It doesn't mean anything for functions in general.
So it's
But for solutions to a differential equations, if it's 0 at even one point, it has to be 0 at all points. So for a solution set to a differential equation, Wronskian 0 means linearly dependent. Wronskian non-zero means linearly independent. And I'm about to show you guys that, in fact, we can. There's a nice proof of this. There's like a formula called Abel's formula or Abel's formula that shows this to us. But your question's a good question. It's where we're going next. Oh man, I probably have said too much. Well, I would have liked to have a little. I think I've spent too much time on the theory. I'm sorry, guys. If it's any consolation, I'm almost out of theory. So. Or maybe I should say, if it's any consolation, I have in the past spent 2 hours talking about this. Does that make you feel better? Maybe. Okay, so like I've just been working through. I've been working through this calculation here to motivate the definition of the Wronskian. By the way, here's some formulas for a 3x3 determinant and a 4x4 determinant. I didn't do any of those, but there's the formulas if you want. Here's a definition of the determinant in terms of a wonderful formula that I shouldn't tell you about. I'm misbehaving a little bit. Anyway, let me get past it here. So here's the theorem. If you have these functions, n minus 1 times differentiable, if these are linearly independent on I, then the Wronskian, linearly dependent on I, then the Wronskian is 0 for all x. Conversely, if there exists x naught and I such that the Wronskian is non-zero, then it's linearly independent. What's conspicuously missing here is what if this is zero, like the converse direction? Like what if you have the Wronskian 0 for all x and I? Does that imply linearly dependent? And like we just showed you the example, no, it doesn't. For general collections of functions, but moving forward here, this is the theorem about a solution set. If we have an nth order linear differential equation and we have solutions to the differential equation. Okay, these aren't just any functions, these are solutions to a differential equation. And if the Wronskian is non-zero at one point, it's linearly independent. On the other hand, if there exists an x naught such that it's 0, then it's linearly dependent. The proof for n equals to 2 is right here. So suppose you've got continuous functions, right? And you've got solutions. So what does it mean for them to be solutions? For y1 and y2 to be solutions to the differential equation, where's my differential equation? Right out here. So the differential equation, I'm looking at second order case, right? So the differential equation, I've got it up there. It's a naught y prime prime plus a1 y prime plus a2y equals to 0, all right? So this is the differential equation I'm looking at. I'm supposing that I have two solutions to this, right? So if I put 1 here, 1 here, 1 here, if I put 2, 2, 2, it works. They're solutions. You plug them in, they work. So what you do then is you look at the Wronskian. So the Wronskian of y1 and y2, right? What is it? Well, it's determinant y1, y2, y1 prime, y2 prime, which is, by the way, y1, y2 prime minus y2, y1 prime. All right? So that's the Wronskian for two functions. And I take that and I differentiate it. Now, if you look at that, I got 4 terms. Why do I have 4 terms, guys? Tell me. Differentiating this, why do I get 4 terms? Yeah, 2 product rules, right? 2 for each. But what happens is something happens pretty cool. You notice that you get this guy and that guy, and these are just multiplications. They're the same thing. They cancel, and you're just left with y1, y2 prime prime minus y2, y1 prime prime. But y1 prime prime and y2 prime prime, you can solve this for y1 prime prime. Like, you know, this, plug in 1 here. So I can solve this for y1 prime prime. That's what I do. See? y1 prime prime, and likewise for y2 prime prime, I get that. Now I take those and I plug them up in here, like so and like so. And then do a little bit more algebra. Some stuff cancels, right? Check it out. Like this y1, y2, y2, y1, minus, minus, plus, just minus, minus. So that term and that term cancel. And you're just left with a minus a1 over a naught, y1, y2 prime, minus y2, y1 prime. But that, my friends, is the Wronskian. So we have minus a1 over a naught times the Wronskian again is equal to the derivative of the Wronskian. Sweet. This is a first order. I don't know if I'm allowed to say sweet. I'm not sure that my life experience permits that. But anyway, sorry about that. But it's very keen. No, I don't think I'm allowed to say that either. That's really before my time. I don't know what I should say. Yeah, anyway, it's a cool equation. So w dx y w prime is equal to, I'm missing a minus here, guys. Come on, minus, 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 minus here, minus here. It came back here, check it out. So integrate both sides, use separation of variables, and this gets you that the Wronskian is equal to some constant times the exponential of the integral of the ratio of the first coefficient function to the zeroth coefficient function. That makes sense because we assumed the zeroth coefficient function was non-zero on the whole interval. If it wasn't, we'd be in trouble. But that is Abel's formula. And what does it say? Think about it. If the constant is 0, this is 0 everywhere. But if the constant's non-zero, it's non-zero everywhere. So that's this formula, which is very much based on y1 and y2 being solutions to the differential equation, forces the Wronskian to either be always 0 or always non-zero. And so the subtlety of the example I have under this projector screen is gone in this case. You're like, well, you just proved it for n equals 2, right? But you're claiming it's holding for n equals to n. That is true. It is the next page. Here's the proof in the nth order case. Abel's formula continues to be true. After a rather dastardly calculation, you can show that the derivative of w is in fact still minus a1 over a naught. It only depends on the first and the zeroth coefficients of the nth order ODE. Very cool. But also, don't worry, not on the test. Nor do I even expect you to read it, honestly. You can skip it if you want. This is an example of something I love called tensor calculus. So anyway, that gives us the theorem that we wanted. And while I got this thing out here, our next theorem is that, in fact, let me just get to the point here. So now we have a tool to check for linear independence. We just use the Wronskian for a solution set. All right? You have some homework on those. It's really just a straight calculation. Now you understand. I hope you understand. You start to understand why. This is another theorem. If we have the nth order linear differential equation on the interval I, then there exists a fundamental solution set. A fundamental solution set is kind of what it sounds like. It's a solution set. What's the fun? The fun is that it's linearly independent. Linearly independent functions are fun. It's not very convincing, but that's what the definition of fundamental solution set is. It's a set of linearly independent solutions, as many functions as the order of the equation. So for a second order problem, 2 functions. Third order problem, 3 functions. Fourth order problem, 4 functions. 4 linearly independent functions. But here's the theorem. If you have an nth order problem, there exists a fundamental solution set. Now this we prove from the theorem that I wrote up here a little bit earlier. Basically, what you can do is just look at the initial data, 1 and then all zeros, or the derivative is 1 and everything else is 0, or the n-1th derivative is 1 and everything else is 0. If you look at that data and you look at what that says about the Wronskian, I mean, okay, first of all, the existence and uniqueness theorem says such functions exist, right? So then when you put those functions into the Wronskian matrix, it gives you back this thing here. Maybe you guys remember it. I don't know. Do you guys recognize this matrix? Right, that's the identity matrix. The determinant of that's 1. So the fact that you can get any initial data that you want means that you can make the Wronskian matrix become the identity matrix, which is 1. Consequently, these functions are linearly independent. Being that they're a solution set, linear independent, I mean, the fact that this is non-zero at one point implies it's non-zero at all points by Abel's formula. Consequently, we have a fundamental solution set. So, finally, let me put this away. Let me just tell you. So if I'm crunched for time, I just say read this stuff, and I just say what I'm about to say. But that's not good. It's good for us to have this discussion because these things are not familiar, and you should understand what we mean by linear independence at least a little bit. It is subtle. But here's the theorem, ultimately. If L of y equals to g is nth order linear ODE with fundamental solution set y1, y2, yn, and if yp is a particular solution, then the general solution to L of y equals to g is y equals to c1y1 plus c2y2 plus plus cnyn plus yp. I need to unwrap the terminology I just used for you guys. So what I'm telling you guys now is what we're looking for in general. We're looking for, there's a couple things we have to do to solve the non-homogeneous problem. So if g is not equal to 0, this is the non-homogeneous problem, all right? Most of your homework that's due Tuesday is a homogeneous problem. You should be able to do all those problems at this point. The non-homogeneous, I'm not sure I have time today to do enough for you on that. And so, we'll see where we get to. But no, I already know. I'm going to push the homework back to Thursday. So I hope that's okay with you guys because of my poor planning. So, yay. We're always going to ask you questions about stuff to distract. I shouldn't give you guys ideas. Fundamental solution set. These functions are not solutions to the differential equation we're trying to solve. I'm still using this terminology up here, guys, okay? So, in fact, they're solutions to a corresponding homogeneous problem. So, the fundamental solution set for a non-homogeneous ODE, they're actually solutions to the corresponding homogeneous problem, all right? But they're also linearly independent solutions to the corresponding homogeneous problem. The particular solution is what it sounds like. I was using that terminology a little bit earlier today. These ones actually return UG, right? So the theorem is that the general solution can always be written like this. This comes shortly after the theorem I just wrote, but I think I've exhausted my my time allotted for theory in here, so I'm going to go on to calculations at this point. You can read the rest of my notes to get the rest of the story there, but look, we can calculate what's L of y equal to. L is linear, right? So what happens here? 0. Why are these 0? Because we assume they're solutions to the homogeneous problem, right? And then this guy is g. So in total, we get g, which shows you that this is in fact a solution to the differential equation. And it's the general solution. What we mean by that is that includes all possible solutions by just selecting different choices of the constants. It'd probably be good for me to show you an example of this in action, right? So I got you guys.